Well, thank you very much. I appreciate that, and I also appreciate you coming out this evening to hear more about climate change. I'm going to be talking about what's been going on in the region and globally, and I'll talk a bit about future climates as well, a bit. But within the context of thinking about adaptation, about planning for climate change in this part of the world, the climate that's going to be coming at us in the coming decades, anticipating that with the view to taking steps to minimize the impacts and also to take advantage of any potential opportunities there might be along the way. So I'll give you the take-home message before I get going here. There's a lot of variability in the climate system. It's inherent in the system. But what we've seen over the last century or so and what we expect in the future is this variability has been superimposed upon an increasing trend. And that means the peaks in the variability continue to get higher and higher. And it's those peaks that cause the extreme events. And those are the ones that we need to be anticipating and taking steps to do something about so we reduce the damage. So in the next about 25 minutes or so, I hope to flesh out an explanation for that statement. Okay, climate change science is a very multidisciplinary endeavor. It involves people from the biological sciences, the physical sciences, chemistry, physics, computational sciences, people who are involved in computer modeling, and the earth sciences, people involved in geology and ice core records and those sorts of things. And that's my background. I was years ago a petroleum geologist in Calgary drilling oil wells, and went back to university and started getting involved in reconstructing climate change in the Rocky Mountains over the last 13,000 years ago by getting core samples out of alpine lakes. And it turns out that the geologic perspective is really useful because understanding what's happened in the geologic past, what has driven climate change in the past, really helps explain where we are now and where we're headed in the future. Okay, there we go. So I'm going to be giving an overview, an introduction to climate science with a focus on extremes and variability. I'll talk about some projected future climate situations for the East Kootenays, and these are based on models that have been produced by the Pacific Climate Impacts Consortium. That's the long name. The acronym is PCIC. So when I say PCIC, I mean Pacific Climate Impacts Consortium. And I'll give you some directions where to go online to get much, much more information. I'm just going to scratch the surface. And I'll finish off with some implications for land, water, communities, businesses, and residents in the basin. And a lot of that has been summarized in a document that you have that's been just recently published called From Dialogue to Action. Okay, so I'll start off with looking at a time series of climate data from the Columbia Basin, temperature on the vertical axis, time on the horizontal axis. And the first thing that should jump out at you is that it's a noisy system. It's spiky. There's lots of wiggle waggles up and down in this. And a lot of that short-term variability we know we can attribute to the El Nino, La Nina cycles, but there's some other things that are involved too. But in this short-term variability that's from year to year or every few years, generally less than a decade, in this neck of the woods is about 2 degrees Celsius. That's what we normally associate with the range of climate variability from year to year, which is actually quite a lot. That's the short-term variability, which is superimposed upon longer-term decadal scale variability. And there's a number of different things that can influence that in this part of the world. So you've got short-term variability superimposed upon longer-term variability, which, and now getting to the point, is superimposed upon the climate change trend, which is the multi-decadal to century scale trend that we've been seeing in the basin over the last 100 years and elsewhere around the world. And in this part of the world, we've seen an increase in mean annual temperature from about between 0.7 and 1.7 degrees Celsius, average about 1.5 or so. And the significant piece about that is that it's almost double the global average. So we've been warming up here significantly faster than the global average. Okay, so now I'm going to look at a global reconstruction of temperature from the 1970s right up to the present. And this was put together by a group at Berkeley, the Berkeley Earth Surface Temperature team. And you can see from 1970 to 77, there wasn't much warming. Same between 77 and 86, between 86 and 95, between 95 and 2001, and then There hasn't been much warming for the last decade either. And you could sum this all up and say, well, there's been no warming. But that would be losing sight of the fact that it's the variability that you would be paying attention to, and you would be missing the long-term trend. So climate, you wouldn't expect it to increase monotonically to any driver, and it has gone up in steps. And this is really key for differentiating between the long-term trend, climate change trend, which we see here, and the shorter-term variability. And again, this is really key to the whole point. There is variability in the system. Just because the climate is being driven in one direction or another, you don't expect the variability to disappear. And that influences extreme events. And here's an example. We're back to the data from the Columbia Basin here. And we choose an arbitrary temperature cutoff. And above this, right here, we've got, I think it was 1938. That would have been during the Dust Bowl era. That was probably the 1 in a 100-year climate event during the Dust Bowl. But because we've got this variability superimposed upon a long-term increasing trend, we've had a number of those in recent years. In fact, they've been increasing in frequency and intensity and in duration. So the key point about climate adaptation is these extreme events that cause the problems. These are the things that cost lives and money. So I'm going to review a bit of basic statistics. This is a bell curve. And you probably remember bell curves from university and high school. If you had 100 students in an exam, you would have most of the students falling around the average mark. Some a bit below, most around the average, and some of the ones a bit above. As you get towards the upper end, maybe around the B+ range, you have even fewer students. And maybe you'd have one genius who gets 99% on the exam. And then where I was, down on the bottom end of the range, closer to the lower part of the bell curve. So the point here is that around the average, where the bell curve is the highest, is where you have the most frequent number of exam results, and it's the same for climate. That can also be temperature, for example. So if we're looking at mean annual temperature, most years fall around the average. That's around the peak of the bell curve. You have a few cold years, you have a few hot years. Now, we'll look at what happens when you shift the bell curve over. This represents climate change over multi-decades, if you like. And what happens when you do that, you shift the bell curve over and you get a new climate that has less cold weather in the tail, but it has more hot weather and much more record hot weather, which is beyond the tail of the bell curve. In technical terms, that would be beyond 3 standard deviations from the mean, but you can think of it generally as sort of more like a 1 in 1,000 event. It's definitely beyond the end of the bell curve, outside the normal range of the climatology. That's not the only thing that can happen. You can also alter the variance or the variability of the climate. So you have fewer years around the average, but you have more cold years and you have more hot years. And some people have referred to this as global weirding. So you have more strange weather, more extreme weather. And if you just increase the variance, you get more cold and more hot weather in roughly equal proportions. Okay? So now we're going to look at what happens when you do both. First of all, you increase the variability, you flatten out the curve, so you have more extremes, and then you shift the mean over. And now what happens is you end up with a new climate that has still some of this cold tail that they used to have in the historical climate, but now you have much more hot weather and much more record hot weather that's beyond the tail of the bell curve. Okay? So this is hypothetical. And what we'll do now is shift to what northern hemisphere land surface temperatures look like, starting with, on the left, the base period, the 1951 to 1980 period, which you can think of as 20th century climate. 33% cold is blue, 33% white is normal or average weather, and 33% red is warm. And you can see decade by decade, the climate, the bell curve has shifted over to the right, okay? So this is real data measured by MET stations around the world. And there's also some indication that the curve has flattened out, that the climate has become more variable as well. And the importance of this is if we go back to the 20th century climate, when you're beyond the end of this bell curve, you were looking at climate events that maybe on a given year covered 0.1 or 0.2% of the surface of the planet. In the last decade, those extreme events covered anywhere between 4 and 13% of the planet. Or you can think of it in terms of frequency. During the 20th century climate, about an event beyond this line would have happened once every 500 or once every 1,000 years. And in the last decade, it happened between 4 and 13 times every 100 years. Okay? And it's this tail here, this red tail, that's beyond the tail of the old climatology. Those are the extreme events that are causing problems. Okay? So now what I'm going to do, I've talked about climate variability when you're looking at a trend through time, and now I'm going to look at the spatial distribution of the warming pattern around the world. So we're looking at maps for a few slides here. And what the Earth's climate system does is it doesn't heat up uniformly around the world. We have weather patterns that tend to bunch up cold and warm air masses. And if we go back to 2003, this is looking at the summer of 2003, first thing you see in the corner is global average above the long-term mean, about ½ degree Celsius above the 1951 to 1980 base period. Here we are in the Columbia Basin. We had above average temperatures 2003. But in Europe, it was under an intense extreme heat wave. And here's the bell curve for Switzerland that summer. We happened to be living in Switzerland summer of 2003, and it was uncomfortable. And like I was showing in the hypothetical case, in the reality here, the 2003 summer was beyond the end of the bell curve in Switzerland. In fact, throughout much of South Central Europe, huge financial repercussions to this, and approximately something in the neighborhood of 70,000 lives lost during this heat wave. So serious repercussions. In our neck of the woods, 2003 will be remembered as the last really bad fire year, and it was warmer than average here. Okay, so we'll skip ahead to 2010. In the Columbia Basin in British Columbia, southern British Columbia got off scot-free for fires that summer, but there was a whole bunch of fires in the northern half of the province. And it shows up kind of nicely in the temperature records here. But the red blob showed up over the Moscow region, summer of 2010. And again, here's the 20th century climatology for Moscow. Here's 2010. Again, another example where that heat event was right off the tail of the bell curve. And again, large loss of life and huge problems with forest fires throughout the region. Skipping ahead to 2011, I think BC's biggest export 2011 was, for the summer, was firefighters. They were all going out of province to fight fires elsewhere because we were relatively cool here. But in Texas, they had an unprecedented fire season. I think over $5 billion lost in the agricultural sector. That persisted through the spring of 2012 in what was a monstrous heat wave centered over eastern North America. NASA actually ran out of colors. They had to lump between 4 and 11 degrees Celsius into the one dark red color here. And it was an exceptional heat wave, but it happened in late winter, so it really didn't, there was no loss of life. It was just kind of pleasant to be playing Frisbee in your shorts in winter in eastern North America. But that persisted through last summer, and the drought conditions in the US last summer were particularly bad. By October, we had 66% of the counties in the US declared as natural disasters areas due to drought, and in some cases flood and drought. So the point of all of this is that there's variability through time, there's also spatial variability, but the odds have now increased that these events, these extreme events that are beyond the end of the bell curve are going to be happening more frequently. They already are happening more frequently. They've been happening more frequently in the last decade than they were in the 20th century, and we can expect this trend to continue into the future. And it's these events we have to be thinking about when we're planning for climate change adaptation. And the last one I've just thrown in here just happened last month in Australia. They had a monstrous heat wave in Australia, and the Met Office in Australia had to add 2 purple colors to the top of their charts to reflect temperatures above 50 degrees Celsius. So a lot of these are things that we can measure. Things like temperature over land, temperature over oceans are increasing. The humidity of the atmosphere has increased about 4 to 5% over the last 100 years. Sea surface temperatures are going up. Ocean heat content is going way up. And we can see this in some of the environmental indicators as we look around. Glaciers are receding rapidly worldwide. They are in the Columbia Basin as well. Snow cover is declining, Permafrost is melting quite rapidly in Arctic areas. We're seeing tree lines shifting poleward and upward. Spring is coming earlier in many cases. Sea level is rising worldwide, and sea ice is declining, and it's declining in the Arctic rather precipitously, and I'll show just one slide that shows this. This is not sea ice extent in the Arctic, it's volume. So when you look at sea ice extent, it's not a great metric because it can be very extensive but quite thin, whereas the volume tells you how much ice is there. So this is volume in thousands of cubic kilometers, and you can see the trend from the 1980 to 2012 is dramatically down and increasingly so. And the one number that jumps out at me right away is 2009. There were 6.9 thousand cubic kilometers of ice in the Arctic sea ice. 2012 it was 3.3. The amount of ice that melted between 2009 and 2012 exceeds what's left. The projections for ice-free Arctic were sometime mid-century or late century, and it looks like in terms of sea ice, the reality is going much faster than the model projections. The insurance industry is very well aware of climate-related natural catastrophes because it impacts their bottom line. This translates into money. Munich Re is a reinsurance company. They insure the insurance companies, and they've been keeping track of natural catastrophes for a long time. And here it's plotted from 1980 until present. And in the bottom here in red is what they're calling geophysical events. Tsunamis, earthquakes, volcanic eruptions, that sort of thing. And if there were changes in demographics that were causing people to move into more hazardous areas, you would expect that to turn up in the geophysical events, but it doesn't. But it does turn up in meteorological events, hydrological events, and climatological events, the things that are driven by climate change. And these are numbers of natural catastrophes, not costs, but actual numbers, and they've gone from about 400 a year to over 800 a year since the 1980s. So far, everything I've talked about relates to what we've seen happen in the climate so far. So projecting what's going to be happening in the future gets a little bit trickier. We have to rely on computer models or climate models. And I always like to point out the first climate model was done in 1896. It was done with pencils. You don't need a computer to do a climate model. They've become much better with the use of computers, and actually the climate models from the 1980s have done a pretty good job of projecting what we've seen over the last 30 years, and they've also done very well at reconstructing climates in the geologic past, so they are quite useful. There's a lot of uncertainty, but there's explicit uncertainties accompany all of those climate projections, and I'll show you a couple of examples. But basically, all of the models are projecting that we can expect this trend that we've seen over the last 50 years to continue into the next century and perhaps accelerate. The different colored lines here are different emissions scenarios, carbon dioxide emissions scenarios for the atmosphere that are used by the Intergovernmental Panel on Climate Change for projecting into the future. And it's broadly accepted that the carbon dioxide levels in the atmosphere is the #1 driver of climate change in the past and what will be happening this coming century. And the black line here is the actual emissions path that we're on, which, with the exception of the 2008 recession, is pretty much approximating the worst case scenario. So it's reasonable to assume that the direction that we're headed is maybe towards the worst case scenario rather than the more conservative scenarios. And to sum this all up, the US National Academies of Science, just in the last couple of years, produced a very large assessment on climate change called Advancing the Science of Climate Change. It's available online. It's a really excellent resource. And I just have one quote from them. Human-induced climate change and its impacts will continue for many decades and in some cases for many centuries. So all indications are that the trends that we've already seen are very likely to continue in the coming decades. And to put this in perspective, I have some reconstructions of climate going back to about 900 AD. So over the last 1,000 years or so, the temperature record, instrumental record, is here in black, and it shows that things were cool during the Little Ice Age, they were warm maybe 1,000 years ago, and we're warming up rapidly now. But to put this in perspective, the temperatures that we can anticipate in this coming century, here's the range. Well, that's where we are now, and here's where we're headed. Between somewhere between over 1 degree Celsius and up to 6 degrees Celsius. So it makes the temperature change that we've seen over the last 1,000 years look fairly small. And unfortunately, because of the emissions path that we're on, we're tending towards the worst case scenario rather than a more conservative situation. And that is now being echoed not just by the scientific community, but some organizations that would normally be considered to be pretty staid conservative organizations like the World Bank, International Energy Agency, and PricewaterhouseCoopers have all released reports in the last 6 months or so that are acknowledging the way we're going now, we're headed for 4 to 6 degree warming this century. So, the Pacific Climate Impacts Consortium has taken these regional global the global models, and they've scaled them down to be more useful for our neck of the woods and other regions, but they've done a lot of projections for the Columbia Basin, and that's what we rely on when we're talking to communities about adapting to climate change in this neck of the woods. And they have a website called Plan to Adapt. And if you go to Plan to Adapt, you can type in your region and the time frame you're interested in, and you'll get reams and reams of information about what we can expect from the climate in the future. And what I'm going to do is just give you a few highlights. Looking at average temperature, annual average temperature by the 2050s, about 2 degrees Celsius. And here's the range, plus 1.3 to 2.8. So there's a fair range, but the mean is about 2.0. An increase in annual precipitation of about 4%. Now we switch to summer. It's actually going to be warmer in the summers according to their projections, 2.3 degrees Celsius, but less precipitation, minus 8% in precip. Looking at winter, 1.9 degrees Celsius warmer, but more precipitation, 11% more precipitation in winter. But at the valley bottom locations, more precipitation is coming as rain and less as snow. And they've broken this down in terms of seasons for different time periods. I just included the 2050s and spring just because this is such a dramatic change. That's when we're really going to see in the valley bottoms a lot less snow and a lot more rainfall. This can all be sort of considered on the negative side of the ledger. There are some potentially positive outcomes. Annual growing degree days are increasing significantly by almost 350 growing degree days. Annual heating degree days are down by 700 or so, and annual frost-free days are increasing by about 25 days. So if there's enough water around, this could be a potential bonus for local agriculture. There's another report that's just on the verge of coming out. This should be hopefully within the coming month or so from PKIC, and it will also be on the CBT website when it comes out. It's called Climate Extremes in the Canadian Columbia Basin, a Preliminary Assessment. And I'm just going to include a few highlights because this is where it really becomes important for climate change adaptation, is focusing on the extremes. And PKIC has come up with some projections for extremes in the coming decades. And by the 2050s, we're looking at up to 4 times as many warm summer days and nights in the Columbia Basin. The maximum the hottest temperatures of the summer may increase by up to 4 degrees Celsius. In the Nelson area, it's 38, going up to maybe 42 degrees by the 2050s. And extreme events in general are expected to increase in frequency, intensity, and duration. And again, if we're looking at either precipitation or temperature on the vertical axis and time on the horizontal axis, when we look at the climate of the 20th century with fairly infrequent extreme events, we can expect those to increase. And again, this comes back to the fact that we have this variable system that's superimposed upon a steadily increasing baseline trend. So PKIC is suggesting that we may be looking at a 2 to 11-fold increase in the occurrence of 25-year record extremely hot days. And in terms of precip, a 2 to 3-fold increase in the frequency of extreme precipitation events with 5, 10, and 25-year return periods. Okay? Now, a document that was just published recently, Dialogue to Action, has taken these climate projections, and I think you should all have a copy of this. It takes these climate projections and translates them into potential environmental changes, and then goes through sector by sector various sectors that you can find in the Columbia Basin. And I've included transportation in this example. And so they've looked at spring flow, flooding, freeze-thaw events, avalanches, wildfire risk, all sorts of things. And They've also included in this document some potential adaptation strategies for dealing with these environmental changes, and they've done it sector by sector. So here's transportation, and here's infrastructure, for example, but they've also been looking at water and watersheds, food and agriculture, tourism and recreation, forestry and mining, health and safety, and transboundary flood control and hydroelectric power. So this is a very useful document for having a look at for how these environmental changes may impact individual sectors. And one example that shows up in a lot of these different projections is landslides. And I really didn't think too much about landslides until this year. And a fellow in the West Kootenays, Greg Utzig, he's a consultant who does some climate work, has put together precipitation record for northern Kootenay Lake. And you can see there's the mean, about 61 millimeters for June. And here's 2012, 228 millimeters, June 2012. It blew the record out of the water. And it increased soil moisture, decreased soil strength, and resulted in landslides. And some big ones made the news, the Johnson Landing landslide, which resulted in some fatalities. There was a few others that made the news, but in a recent emergency management BC workshop that we did, we heard about all the other ones that didn't make the news. There was a lot of landslides this spring that were related to these extreme precipitation events. Other environmental changes that are occurring rapidly here as well as worldwide are the recession of glaciers. This is the Kokanee Glacier in about 1870, and there the blue line is where it is now, and it's receding rapidly. And this is shocking if you spend any time in the Alpine. This is occurring within our lifetimes, but these also serve a function. The glaciers work like water towers. In late August, when it hasn't rained for 4 weeks and all the snow is melted, in many stream systems the water is coming from melting glaciers, and as the glaciers get smaller, it may impact the hydrology. And I'll show you an example of some hydrology here. Another thing that can impact the hydrology is April 1st snow extent. So here's the current April 1st snow extent, and here's projected less. But the other thing that should jump out at you here is this is potentially a transborder issue. Most of this problem is happening south of the border, and the Columbia Basin Treaty is being negotiated right now, so this can get complicated. But what we're looking at here is a hydrograph. This is flow in the Columbia River, so it's low through the winter, it peaks during spring, and it falls off during the summer. That's the 20th century flow, and what's anticipated because of earlier snow melt, more winter precip as rain rather than snow, is that you may have higher late winter flows, a lower peak in the spring runoff, and then late summer you may have lower flow, and this can impact agriculture, hydropower, and municipal water supplies. And the town of Kaslo was involved with adaptation planning. It started a couple years ago, and Hans Schreier was involved in this one. They identified their water source as a potential vulnerability, and there was a couple of models around here, a blue one and a red one, starting back in the 1950s and projecting out into the future. This is percentage of available water. The big red line is 100%, so if you're above it, your demand is exceeding supply. And so it became clear to the community of Kaslo that they were facing a problem. And so this is how adaptation works. They identified this as a vulnerability. They looked into the crystal ball to project the future, and then now they're taking steps to reduce consumption and look at improving their water supply. This is a paper that was just published. It's not even in print yet. It's online, and it's going to be published shortly. I just came across this 2 days ago, and it shows the correlation between increasing temperatures and intense rainfall events. And this is something that's been suspected, but this is the first time it's been quantified. 8,000 meteorological stations around the world. The blue dots represent locations where there was a positive correlation between increasing temperature and intense rainfall. And the bottom line from this paper is that there has been a 7% increase in extreme rainfall intensity for every degree increase in global atmospheric temperature. And so what we're anticipating this century in this neck of the woods by 2050 is about a 2-degree rise, so we can expect more intense rainfall events. And there was one in this neck of the woods. These are pictures from Cranbrook last summer, very intense short rainfall events. In Nelson, we've had a number of these in recent years where Warden Baker turned into a river and lots of damage. And it's something that some municipalities are now flagging as a priority, the stormwater management. And lastly, wildfire. In this neck of the woods, we live in a potentially very flammable environment, especially over in the West Kootenays. in the interior rainforest, when it dries out, there's a lot of fuel there. And when the situation is we're looking at potentially longer, hotter, drier summers, which translates into potentially worse fire seasons. When an interface fire gets into a community, it can be devastating. So I think some communities are now really beginning to realize we need to be taking action to reduce the fuel loads around our communities. So to sum up, I think some of the important takeaway messages here are it's really important to pay attention to distinguish between short-term variability and the long-term trend. And the short-term variability that's superimposed upon the long-term trend is what leads to these extreme events that we have to be anticipating. And all indications are that that trend is going to continue into the coming decades. And the communities that are able to look into the crystal ball, to identify the vulnerabilities and which sectors are going to be impacted by these changes in climate are going to be the communities that are likely to be the more resilient and sustainable communities of the future. Great. Well, thanks for your attention. And I think what we'll do is we'll switch right over to Hans here to pick it up, and then we'll have time for questions afterwards, right? Okay.